Today we will be looking at sequence to sequence encoder. Sequence to sequence encoder decoder is a neural network and we can apply the task of machine translation to it. As we see in this image, an encoder RNN has a sentence I am a person which is coded into Je suis une personne, which is a translation of the given sentence to French. And then we use a decoder RNN for understanding it at the other end. Encoder decoder architectures are about converting anything to anything, including machine translation and spoken dialogue system, image captioning and image teletexts, which uses convolution encoder and recurrent decoder, generating images by captions, which uses recurrent encoder and convolution decoder, and such various other conversions of words to transcripts. Our task today is the machine translation. We will be encoding and decoding models on Russian to English machine translation problem. More specifically, we'll translate hotel to hostel description. This task shows the scale of machine translation while not requiring us or requiring you, the learner, to train your model for weeks if you don't use GPU. Before we get to the architecture, there are some pre-processing to be done. This pre-processing has been done in this lecture, but the further steps we expect you, the learner, to do it by yourself and learn. The data is tokenized using the word punct tokenizer. However, there's one more thing to do. Our data lines contain unique rare words. If we operate on a word level, we will have to deal with a large vocabulary size. If instead we use a character level models, it would take lots of iterations to process a sequence. This time, we are going to pick something in between. One popular approach is the byte pair encoding. We have come across this in the previous video lectures, but here's a brief about it for recollection purpose. Byte pair encoding algorithm starts with a character level tokenization and then iteratively merges most frequent pairs of for n iterations. This results in frequent words being merged into a single token and rare words split into syllables or even characters. We install the PyTorch and the subword NMT for the purpose of this lesson. And then, like we have done before, from the NLTK toolkit, that is natural language toolkit, we import a package that is word punct tokenizer. And from the subword NMT, which we previously installed, we import the byte pair encoding. For the preprocessing, we split and tokenize the data. And then we build and apply byte pair encoding vocabulary to it. Splitting and tokenization of the data is, as we have done previously, splitting of the data is for every space that we encounter, indicating the next word. We now need to build vocabularies that map strings to token IDs and vice versa. We're going to do this by training the data to a model and converting the output matrices into words. We will be importing the NumPy and the Matplotlib libraries. We use the NumPy library to split the array from sklearn package. We import the train and test split for training and for splitting our data into train set and test set. For converting lines into IDs and backwards, that is vice versa, we first take the batch lines and sort the trained input for the given length. We then convert these batch IDs in the input vocabulary to matrices. The batch lines are restored by converting the input vocabulary into lines, that is batch IDs. So we have converted it back and forth between cast lines and IDs. We then draw a source and translation length distribution to estimate the scope of this task. The code below contains a template for a simple encoder-decoder model, a single GRU encoder-decoder, nothing special as such. It's just a basic template. This model is implemented as a reference and a baseline. We import the torch library which we had previously installed in the beginning of this lecture. We use a simple encoder-decoder sequential model. We initialize the base class to track sublayers, parameters, etc. We then apply a model to train the mode, which is done in the forward function. In the encode function, we take symbolic input sequences, compute initial states as input parameter, which are matrix of input tokens, and return initial decoder state tensors, one or many, maybe one or many. We have the encoder sequencer as batch, time, and size. Last state, note that the last state is not actually the last state of the padding. Let's find the real state. In the decoding step, we take the previous decoder state and tokens and return new state and logits for the next tokens. The parameters of the previous tokens are a list of previous decoder state tensors, which are same as returned by the encode, and parameter previous tokens, which are previous output tokens, and int vector of batch size, the given batch size. Then we return a list of next decoder state tensors, which are a tensor of logits for a given batch and length of the output vocabulary. In the decode function, similar to the decode step function, we iterate over reference tokens of output tokens with decode step. With initial logics, we always predict the basic output systems. The decode inference function is used to generate translations from model, which is a greedy function because it finds ways to maximize the output. We then append all the output logics together and we translate it using the encoding the input. In the debugging area, we use the dummy input tokens where we convert input vocabulary into matrix. We have noticed that previously, while converting the input vocabulary to a matrix, we had done it in three different lines, but here in this scenario, we have merged all of them into a single line. We convert the dummy output tokens as well into matrix, so the both the input and the output dummy tokens are in the matrix form right now. We encode the dummy input tokens. Then we make sure that the length of h1 here is the decode step and h0 is the encode step. We make sure that the length of the h1 and h0 remain the same. And then we go to the next logics and so on. We try to do the same for the rest of the iterations. We then use dummy translation for the dummy states and translate the lines. Our training objective is almost the same as it was for neural language model. This is a basic formula, but for the understanding of natural language processing, this step can be skipped. Computing the loss, we can use the above formula for computing the loss, but we don't need to remember these formulae as these can be these are predefined in certain functions which are present in the natural language toolkit library.